So this is a talk by a colleague, Nirav Dave and me at SRI. Um, Nirav has been working on processors and hardware, and I'm a software guy who's just starting in hardware. I built a OpenFlow network switch, but this is my first processor work. This is something that we've just started. It's more of an informational presentation. And the goal is that in the software world, there's been an increasing trend of verified software for critical parts of the software toolchain. So you have verified compilers for C and ML. You have operating systems, you have hypervisors, and this is to get a handle on the vast amounts of buggy software and security problems in the software world. Unfortunately, all of these have a catch. They assume that the hardware is correct. And in the real world, so take the hypervisors that I implement on x86. In the real world, you have this. The Intel errata sheet from March 2015 has these kinds of bugs. Some instructions may report a wrong address when an interrupt or exception occurs in 64-bit mode. Various instructions may cause a hang. Accessing memory may cause unpredictable system behavior. Processors may enter shutdown unexpectedly. So this is from March 2015, and there are 140 items in that specification update, and all have been marked no fix. There are no plans to fix any of this. But this is Intel. We know Intel is a complex processor. It could be better in the ARM world. Unfortunately, it's not much better. This is the Cortex A53 errata sheet from this year. You could get corrupted instruction streams. Various instructions might produce incorrect results. Loads in stores might access incorrect addresses. You might have misaligned PC and out-of-range address aborts, and you could go to the incorrect exception level. And this goes on for 37 pages. And the question is it going to be any different for RISC-V? So the thing that we're trying to do is try and make sure that we have a much better situation with RISC-V. Now, what are the minimum things we can do for a verified RISC chip? We need an unambiguous formal ISA specification. And this needs to be coupled with a processor implementation that you can kind of verify that it implements this formal ISA spec. And you need to prove that there's a link between the actual processor implementation and the formal ISA spec. So this is just work that I've been doing to try and address these portions. So I've been working on formalizing the ISA spec, and Nirav has been working on a processor implementation. And we'll eventually try and bridge the two gaps, but this is two independent pieces of work in one talk. So let's get to the formal ISA spec. So the way I've been doing it is trying to use the L3 DSL, domain-specific language for specifying instruction sets. It's a nice DSL from Cambridge. It allows you to specify an ISA and then use the specification for two purposes. You can generate an executable version, an executable interpreter for the ISA, so you can actually run binary code using that interpreter. And on the other side, you can generate formal definitions for a theorem prover. And the theorem prover it currently uses is Hall 4. And right now I'm using it as the interpreter as a reference oracle for processor. This is not fully done yet. I'm just trying to make sure it executes existing RISC-V code properly, especially the RISC-V tests. A little bit about the L3 DSL. It has high-level constructs for registers, instructions, this global state that you have in the processor. You have ML-like data types. It's got extremely strong type checking at a bit level, so it really helps you catch any bugs that you may have made in your specification. It's got a library for bit vector operations, for floating point, and things like that. So the current status of the of this formal spec is it's almost done with the privilege spec. It implements interrupts and virtual memory. That just got done on the weekend a couple of days ago. It's not optimized yet, so there's no cache instruction or data cache, so it runs extremely slowly when you're running virtual using address translation. And it's currently passing most RISC-V tests. It started passing another test after a clarification last night. So this is currently available on GitHub. You can take a look at it. And like I've been pestering the ISA dev list with some requests for clarifications in the spec. And so I think hopefully the spec will improve with more eyes on it. Similarly, I hope that this formal spec improves with more eyes on it. So you're welcome to take a look at it and see whether it makes sense and send improvements. So a couple of clarifications that perhaps the spec can address. When you have a pipeline processor, you could have a synchronous exception that comes from the pipeline, and you could have an interrupt that comes to the processor from the outside world. Which one does the processor service? It's not clear from the spec. Yeah. It would be nice to have some guideline on what the processor should do. This was something that occurred yesterday, and it got clarified overnight. So, but the spec doesn't mention that a misaligned fetch is trapped before any side effects from a jump and link instruction. So it could be, and other simulators for RISC-V are making the same mistake, because the spec is not clear. So the next steps that the spec, that this formalization effort is just basically to complete the specification. It needs to handle the RVC instructions, floating point, the SBI spec when it becomes available, and then we can think of booting Linux and FreeBSD using this formal spec, and tie it back to the processor implementation that we have from BlueSpec. As they presented in the first workshop, they have a tandem verification setup where you can use a reference C implementation, a C simulator, to actually verify the BlueSpec processors. And we want to see whether we can use this formal spec to perform the job of the C simulator. And on the other side, on the formal side, we're going to take a look at exporting Hall 4 formal definitions of the ISA, try and prove, as was mentioned, there's effort to port cell 4 to RISC-V, and there's some interesting properties of cell 4 we could prove using a formal spec like this. Things like the user level processes do not modify privileged state, and there's no leakage of privileged state to user level processes. And then tie this to, use these formal definitions to generate architectural predicates for hardware processors. This will become clear in the next portion of the talk, where I'll be presenting Nirav stuff, the stuff that he's been working on. Nirav is trying to make sure that we can verify implementations of an ISA. So you start with an architectural spec, you have a microarchitectural implementation of that spec, and then you want to make sure that the two are in sync, and you want to keep that synchronization established and robust to any changes in your implementation of the design. And you want to make it quick, and you want to make this usable by architects, not necessarily only formal methods people. And the actual implementation we are trying to target this for is designs in BlueSpec Verilog. And BlueSpec has kindly given us their implementation of RISC-V, the Flute processor, which is what Nirav has been using. So in BlueSpec Verilog, you break the implementation of an instruction into smaller transactions. Each transaction is basically you read some state, you operate on that state, and you write that state back into the processor. And you use smaller transactions so you can do more in a single cycle. So you can reorder operations, you can perform speculation. The basic idea is the transactions in the design map to rules in BlueSpec Verilog. And design correctness is it can be inferred from the rearrangement of the micro transactions into ISA level operations. So in the pipeline view of the processor, the stages execute in reverse order. So basically, the write-back stage cleans out a FIFO into which the memory stage writes. The memory stage cleans out its own input FIFO, and it goes in reverse order up the pipeline. That allows you to execute multiple instructions, different portions of instruction in parallel. In the ISA view, what's happening is that an instruction enters the pipeline at the beginning and goes through the entire pipeline and then exits, and you get a committed instruction. So the architectural view is at the ISA level, instruction level, and the pipeline view is at the microarchitectural level, and you need to find a mapping between the two. The pipeline correctness is derived from the fact that you can actually commute these rule execution orders. Now, this is something I haven't fully understood and I can't explain it, but Nirav will have the details. Two rule sequences, two implementations are equivalent if they start and end in equivalent states. So this is a notion of bisimulation that you find in various fields. But the problem is that what happens if instructions are partially executed. And for partially executed instructions, what you have to get to an ISA meaningful state, so you flush the pipeline. To formalize this technique, you basically need a predicate on microarchitectural states which picks out states that make sense at the ISA level. So the architect of the processor provides these predicates manually, and it's something that architects can do. It's using a vocabulary that is architect-friendly. It's not tied to any formal methods vocabulary. And the idea is that you search for all possible microarchitectural traces, executions that start in a ISA level state and end up in a ISA level state. And the ISA level states are picked out using this predicate. So basically, it's performing a stuttering bisimulation search. So at the microarchitectural level, you're going through a series of states. At the architectural level, you're going from one state to eventually a different state, but in the middle, you are repeating the same state. So it's stuttering. It's repeating the same state until you get to the next state. So that's stuttering bisimulation search. And this is what the tool does. It performs this bi-simulation search. And so it can handle, if you make any changes at the microarchitectural level, it will, as long as the predicates don't change, this thing will just pick up whatever changes you made. You don't have to change your predicates. So it's robust to any design changes. Now, it doesn't guarantee the correctness of that you've implemented the right ISA because you've provided the predicates manually. And this is the gap that we are trying to fix with the formal ISA spec. We want to generate these predicates automatically. So so the expected traces will basically, for a single instruction, you'll find all the various stages of the pipeline showing up in the trace. For a branch misprediction, you will find one instruction that's partially executed before you decide it was mispredicted, and by the time you realize that, there's another instruction that's entered the pipeline. A bug in the pipeline manifests by the tool telling you that there's no way it can fit a sequence of microarchitectural state changes into a state change from a single ISA level state to another ISA level state. So it'll show you the sequence that don't map into this, that don't fit this mapping. This has been going on the Flute Microarchitecture, which is analysis-friendly pipeline design from BlueSpec. It has modularized pipeline stages that allow for changes in pipeline timing. The current status is Nirav is working on basic correctness. The design uses R wires, I think, to improve timing, but Nirav is trying to make sure that if you replace those by FIFOs, you maintain correctness, and the goal is to show that this processor pipeline is equivalent to an unpipelined processor. So there are no bugs in the pipeline. The eventual goal is to fully abstract this this pipeline processor to an ISA level design, and then but this will still be using predicates that Nirav defined manually, and the next step would be to use the L3 specification to automatically compute these predicates. These are the two branches, and hopefully the goal is that we'll eventually merge these two branches and have a processor that's verified at the BlueSpec level. There's another story of what happens from the BlueSpec level to the Verilog level, and then way beyond until you get to the actual silicon. So that verification path is a major challenge, but we're starting at the high level, ISA level first. Any questions?
So one question I have is, do you think it's possible to take the formal spec and generate a textual, human-readable document from there?
It may be possible. I think the way it can be used is for complex instructions, it would be nice to have some pseudocode that other ISA specifications use, like the MIPS ISA has pseudocode explaining what's happening, and it could be used to actually just transcribe the formal spec into text, and you get pseudocode. But automatically generating text is a different story.
Rishi or Nikhil from BlueSpec. So in an offline conversation, you had mentioned that L3 is very good at for specifying the processor pipeline, but not so good for the memory system side of things. So what do you see?
Actually, it doesn't. It's good for specifying ISAs. So the primitives that the language has are instructions, registers, and some state variables. So it doesn't have any concept of pipeline. So you could implement a pipeline in L3, but you'll have to do it manually, but in terms of your own encoding. But it naturally helps you specify a single cycle simulator.
What about the memory system? And
Yes, that is, it does not capture any, there are two things it does not capture: your interaction with memory and any concurrency in terms of a multi-core implementation. So the scheduling of cores would have to be done manually outside L3. So you can attach standard ML code which will do the scheduling for you. You can attach standard ML which will, it'll perform any memory interactions, but that is outside the L3 model. So when you export that to a theorem prover, you won't get any of that stuff because it's in standard ML, it's not in L3. So I understand the group in Cambridge is working on improved tool that will help capture memory interaction, but it's not yet available.
And is this true of alternative tools, or is this, I mean, you chose, I'm not sure why, what guided the choice on using L3 particularly?
The reason I chose L3 is because it's been used to get formal properties of ARM v7. And I think the people who used Cell 4 also used tools that were derived from L3 models of ARM. And I'm not aware of other tools that allow you to generate both an executable specification as well as export to theorem provers.
Okay, thanks. One question I had though is, do you think you could compare the complexity of the ISAs by comparing the complexity of the formal model?
Yes, I think you can do that. So for example, this effort was started by porting the MIPS L3 specification, and it is definitely much simpler. The RISC-V specification is much simpler than the MIPS. So I don't know if you can directly see it from the lines of code, but if you try and read it, it should be obvious that it's much simpler.
How does the ARM version compare?
There is I say spec for ARM, but I don't think it is complete. So it's not easy to compare.
All right, great, thanks.